All right, so today we are starting chapter 3, and chapter 3 is on exponentials and logarithms. And I know that you've done this in, well, ideally you did it in Algebra 2, you've done it in college algebra. Some of this will be the same, but we are going to amp it up a little bit in PreCalc. So let's go ahead and take today, all we're looking at are exponential functions. But before we jump into that, let's just give a little preface of what is coming here. Yes, today we're going to talk about exponentials, but one of the things that we will do a lot more of in this course is we'll do a lot more with applications. And so exponentials are great for any sort of growth and decay. That could be population, it could be a bacteria, could be a disease, different things. Could be money. We're going to spend a whole day talking about money and investments on exponential growth. Okay, the other thing would be, and I'm going to jump down to logarithmic because that's the other one that you should be familiar with. And a logarithmic scale can be used when you're talking about the Richter scale for earthquakes, or a pH acidity scale for you chemistry people. Decibels are measurement in a logarithmic scale. The new one for us is going to be this logistic. We haven't talked about that in previous classes, so this is a new type of thing. And it can be a population growth, but it's a restricted population growth, or a chemical reaction, or maybe the spread of rumors or disease of some sort, because that can be a restricted growth. Now, specifically with exponentials, this is the model for an exponential equation. And this is going to be a model that you're going to need to know. So your f of x, that's like your y value, is equal to a. A is always going to be the initial value. And so you can put that value there. B is the base, or the growth factor. So if B is smaller than 1, then it's going to be exponential decay. But if B is greater than 1, it's exponential growth. If you were dealing with graphs, which you did graphing of these in college algebra, we're not going to spend a ton of time with graphing with paper and pencil, but just you need to have that awareness of what it looks like. So the parent graph for exponential growth looks like this. We use a base of 2, and we assume that the initial value is a 1. It's not even written there. So this is your parent graph. And so here's what it looks like. It has a horizontal asymptote at the axis, and then of course that can get shifted around. That's an exponential growth. Exponential decay would have a growth factor of 1/2 for the parent function. And so you can, again, shift this around, but the asymptote still stays here. This key point, it's not called a vertex, but it's sort of that point that we track as we are graphing. And so that crosses at 0, 1, because, again, the initial value is assumed to be a 1. So that's why that's crossing there. Another thing that we'll quickly refresh your memory on is the natural base. It's E, and there is a mathematician by the name of Euler. His name was spelled actually E, I think it's E-U-L-E-R. I should know that. But it's spelled with an E, and so he made this number, named it E. It's 2.718. So when you think of an exponential that looks like this, if you're using the natural base instead of the base 2, it would look like this. And so the reason that we deal with E is because it does occur in nature a lot, and so we have it in a lot of formulas. It is a button on your calculator. It's over on the left. You'd hit second ln to get that e to the x. Okay, so let's jump in and let's try maybe writing some equations. Now, you probably don't have this slide in your notes, so I'm going to do this one, and then you have the next slide that you have to do by yourself. So on this one, this is going to be the g function. So here's my x, and here's my g of x. So this is basically an xy table. And so the formula that we said previously, if you'll recall there, has the initial value, and then it's the b to the x, like this. All right, so what we're trying to do is write this equation that represents this table, and we have two unknowns here that we have to solve for. We have to solve for both A and B. And so I have numerous ordered pairs that I can use to help me do that, but I'm going to start with the easy one. I'm going to start with 0, 4, because that seems like an easy number to plug in. So I'm going to plug 0 in for X and 4 in for Y. Now, can you see why this is going to work out nice? B to the 0 power. I don't even care what 0 is. I'm sorry, what B is. Anything to the 0 power is equal to 1. So that's just going to become a 1 times A. So I end up with 4 equals A. So now I know what to put right here. I'm going to put a 4 here. Now, I did that, but this is going to be the last time I do that. Because if you think on a graph, I showed it earlier there on that graph, that your initial value is what happens when X is 0. And if X is 0, the initial value would be 4. It just falls into your lap like that. So this will be the last time I go through this. Futuristically, I'm just going to be looking for the 0 term, and I'm thinking, oh, there's my A right there. It's my initial value. Okay, so then I'm back to, okay, so I'm going to circle that. So now I'm back to doing it again, but this time I know that this is a 4. I still don't know what B is, and I've got an X here. Now I'm going to pick another ordered pair. I can't use the same one. I got to use a different ordered pair, and I'm just going to make my life easy. I'm just going to pick the 112. Any of them would work, but there's no reason to make our life difficult here. And so that becomes B to the first, which is just B, or 4B. So I'm going to divide by 4, and B is going to be equal to 3. And once I know what A and what B is, then I can write my equation, G of X is equal to 4 times 3 to the X power. All right, so let's go to the next slide. Now we're doing H of X. All right, the X's are the same, but now you're doing the Y's that are the H of X. All right, this one I want you to do all on your own. Go ahead and pause the video, do what we did on the previous one, and then come back when you're done. Okay, this is what I ended up with. I just knew that the initial value was 8, and then I went and solved for the B. If you've got that, let's keep moving. If not, pause and check out what you did wrong. All right, as promised, we're going to do a lot of applications with these exponentials. And so a classic situation is population growth. So we will assume that growth is exponential. We're going to use this population data. I went and Googled this to find some Wichita populations and found a couple years of data that I wanted to use. And the question ultimately is, when will Wichita reach 420,000 people? Okay, so here's what we're going to do. The first thing that we always want to do is we do not use years as values. We go ahead and we say, we pick a starting year. I'm going to pick 2011 as my starting year. And so that's going to be year 0. 2020 then would be 9 years later. So instead of using that as a 2011, I'm going to use it as a 0. And since it is my 0 value, I then know that this is going to be my initial value. So that's going to be the A value. I guess I got ahead of myself here. What I'm going to do here is I'm going to go ahead and do the exact same thing I was doing on those previous ones, where I'm going to write the model or the equation that represents Wichita's growth. And then I'm going to use that equation to help solve this problem. So right now I'm just writing the equation. So now I know, and I'm going to use a P for population with respect to time. And my initial value is 377,906. And then I don't know what the B value is, and I'm going to raise it to the T power. I'm using a T for time instead of X. Just good to get in the habit of using proper notation for things, depending on what you're dealing with. Okay, so now I'm going to use this other ordered pair. So we're doing the exact same thing, only the numbers are way yuckier, but it all works the same. So that's going to be to the 9th power. So I'm just going to start off. Now, I've already done all the calculations to hurry us along here, but so my first step is to divide by that 377,000 number, and I've got 1.034. Now, I am going to write 1.034, but here's the deal, and I'm going to say this probably 10 times. You cannot round numbers off. Now, you can write them. That's fine. I don't need to see 17 decimal places, but all of your calculations have to use full values. It really makes a difference. Surprisingly, it really makes a difference when you're dealing with exponentials, that these decimal places way out here at the end really do affect your answer. So I'm going to write this, but I will always keep full values in my calculator. All right, so then I've got b to the 9th here. Now I'm just going to take the 9th root of that. Remember, you do that in math, and I believe it's math. I think it's number 5 or something, where you do the 9th root. And I've got a b value of 1.00. I'm writing 367 because it matters when you're getting this small. Okay, now I cannot use this rounded number. I will have to either store this. I'm going to talk about how to store in case you don't know, because there will be times we need to do that, or you just have to go up, 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 up and grab it anytime you need it. But I'm going to practice this storing. So to store this number, I would just hit the STO button, which is just left of your number 1 key on your calculator. If you don't have your calculator, you should grab it out so you can at least follow what I'm doing. Store, and then you can have 26 letters that you can store it under. I'm going to store it under, I guess, B. So store, and then you have to hit your alpha button to indicate that you want to store it under an alphabet number. And B happens to be the apps button. So store, alpha, and then I just say B. Now, anytime I need this number, I would just hit alpha B and it would use that full value. Now, sometimes using the store method is the only option we have. Depending on your calculator, some of you can just go up and grab it, but still there's other times where you have to know how to store. So get familiar with that store button. Okay, moving on. Now, what I have is I have a model that looks like this. Big numbers here. Now I'm going to go ahead and write, I don't know that I have to have all of those. I'll go ahead and write a 4 here, but know that I'm using full values always. Okie doke. So then, and that's going to be to the T. Now the question is, when will there be 420,000 people? Well, 420,000 goes right here. And I'm trying to solve for T, the time. Now we're only dealing with exponentials today. So our method today is we're going to do a quick little graph of this on our calculator. So what I'm going to do is I'm going to type this model into Y1. And this is what I was talking about, where you're going to have the full value of this. You can't put this, you can't put this, you need the full value. So if you stored it under alpha B, then you could type this and then hit alpha B to the T, and that would keep the full value. Otherwise, you're having to write and type that full value, because this is one of the scenarios where you can't just go up, 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 up and grab it, because you're now going to be on our Y equals menu. Okay, so I'm going to type that into my Y equals menu. And then what I'm going to do is I'm also, and I probably, you know what, let's see if I can tweak this. I can. I'm going to change this to Y1, just for the sake of our notes. And then in Y2, I'm going to put 420,000 because that's what I want the Y to actually equal. So now I usually like to see if your method of solving is with a graphing calculator, then I just want to see a quick sketch of what it is you're looking at. So we have to set up a window because obviously these numbers are a mess. So you're going to go to your, after you type these in, you're going to go to window, and my X value, X is my time. I'm not talking to the years. It's 0, 9, and I'm trying to figure out how many years do you think? I'm gonna, I'm just gonna go to 50. I don't want to have to come back and change it. So I'm giving myself to 50. So there's my window for my X's, and for my Y's, I know that I'm looking for when Y is 420,000. So maybe I'll put in 450,000, give myself a little bit of buffer so I can see what's going on. All right. And don't get too worked up about the scale, but I usually try to just think if I'm going 0 to 50 and I was going to make this by myself, this graph, I would probably scale it by 5s, maybe even 10s. If I was going from 0 to 450,000, I would not be going by 5s or 10s. I'd probably be going by maybe 100,000 or something like that, maybe 50,000. All right. When I did that, here's what my graph looked like. Y1 came in here and it was a very slow exponential growth. It didn't really look like exponential growth because it was so gradual. And that's because of the very small b value there. All right, but then the Y2 just gets me a horizontal line at 420,000. And what I'm looking for is when my exponential actually equals that 420,000. So what I'm going to do is then I'm going to find that intersection on my calculator. So to find that intersection, now hopefully this is review. Ideally, you've used your calculator quite a bit, but sometimes, you've maybe set out of math for a little bit. And so you've forgotten how to do some of these things, which is why you really, really should have your calculator in front of you. Even though I'm doing all the math for you, you should be like pushing the buttons and getting familiar with this. All right, so what I'm going to do now that I'm looking at that graph, I'm going to hit second trace. And I'm going to hit number 5, intersect. And then down at the bottom, it says, what do you want the intersection of? What's the first curve? It automatically starts off at Y1. So I press enter. Yep, that's the first curve. Then it's asking for the second curve. It automatically goes to Y2. So I press enter. Yep, that's the second curve. And then the guess, I can just move my cursor close to where it's intersecting. And I press enter. And I have an intersection right here. It is at 24.51. I'm going to round to hundreds here, 24.51. Now, what does that number mean to you? Well, that is the X value of this point right here. And the X values are the number of years since 2011. So it is going to be, oops, I kind of erased that accidentally. That was a 24, or maybe it just got messy there, 24.51. So it's going to happen 24 and a half years after 2011. So then my answer is going to be, well, let's see, 2011 plus 24 is going to get me 2000. What happened to my pen there? 2035. Now, I'm not going to round up on this because it's 24 and a half years. So it's still going to be in that 24th year. It's just going to happen in the summer, right? Halfway through the year. And so don't round up just because it's a 0.5. You're going to leave it at 24 and just add that to your 11. And that's the year that Wichita will hit 420,000. Now, if you were in class, I would have Googled this and looked at what our population was and checked the accuracy of it, but you missed out. So All right, so let's look at another scenario. So that model that we just used 3 times there in a row, that's a very common um, exponential model. Now we do have some special models that we use in certain cases. So here's an example. It's a little fancier looking. This is what we use for a population growth model. Here's your ending population. Yes, that's what we were using. Instead of an A, it's a P sub O. That's the initial population. Yes, that's what A was when it sat there. It was always the initial. But instead of a B value here, I've got this expression 1 plus R. And this is still going to be the growth factor, but it's used when your growth factor is given as a percent. If something is increasing or decreasing by a percent, then that percent rate goes here, but we write it as a decimal. So 5% would be 0.05 plus the 1. So then my B value is a 1.05. That's what's going on there. And then my exponent is still t for time. Okay, so this one says consider a city, Mazopolis. The initial population is 1,000. It's increasing 5% each year. Find out what the population will be in 10 years. Okay, this is an easier scenario than that previous one because we are looking for the population. We're finding this, and they've given us everything we need over here. So all we're doing here, I'm going to squeeze this in up top. We're going to do find the population. If the initial population was 1,000, and then this is a 1.05, and then we want to know what it is in 10 years, so you put a 10 right here. And that one, for whatever reason, I don't have typed in my calculator. So here we go. It's going to be a 1,000 times 1.05. That's not even rounded. It's just exact what it would be to the 10th. And I've got a population of 1,628. It does round to, it's a 28.89. To be honest, I'm kind of a fan of seeing that decimal value and knowing that you got a decimal on it. Now, if you want to come back and you say, I can't have half a person or a part of a person, and you want to round that or truncate it, you can do that. I really look for the decimal answer, and then you can choose to round that up or down. Because you're talking about people, it kind of feels like you should round it down, but I don't get too caught up over that. Give me that decimal, and then clean it up however you want. All right, here's another model. This one is used when you're doing a doubling problem, like if you're trying to double your money, or the bacteria is going to double every year or week or whatever it is. If you are doing a doubling problem, A is still going to be this initial value, but your B value, your growth factor, is a 2. If you're doing a half-life problem, then your B value is 1/2. Half-life happens a lot when you're dealing. I got to think you've done this in like biology or maybe even in chemistry, where you're doing half-life problems, where you're doing like radioactive decay to measure how old a fossil is or something like that. They do half-lives. Okay, I'm not going to teach half-lives. Just assume that you kind of understand that. The only thing tricky here, the only thing that's different is this piece right here that I have starred, so make note of this. If your substance is doubling, so this, we'll pretend it's a doubling problem, could be a half-life problem, but if you're doing it every 3 days, then your time has to be edited. It's not going to be a T because you're thinking of a unit of time. It's in hours, weeks, days. It doubles every week or every year or every 10 years or, oh, wait, 10 years? How do you deal with that? This is how you deal with this. Not everything's going to double or do a half-life in a nice 1 unit of time. So if it's going to double every 3 days, then instead of putting a T here, you put a T over 3, and that's what goes here. You'll have some of those on your homework, so be looking for those to happen. All right. Last problem says, suppose a culture of 10 bacteria is put into a petri dish and the culture doubles every hour. Oh, we're in luck. It's 1 hour, so we don't have to worry about that dividing by something in your exponent. So we have 10 bacteria to start with. It's going to double every hour. We're predicting when the number of bacteria will reach 1,000. And I want you to answer this in hours and minutes. Okay, doke. This is back to a little bit harder problem because you're looking for that time. So here we go. I'm going to start off and I'm going to write my model. And you can use a P for the population of the bacteria. You can use a Y. I'm actually going to use a Y1. My initial was 10. It's doubling, so the growth factor is 2 to the T. That's the model that I'm going to use. And I'm going to have to type that into into Y1 in my calculator. And in Y2, what is it that you want the Y to actually equal? Well, I want the bacteria to equal 1,000. So I'm going to put this in. So this is like the Wichita problem. I'm going to type these two in my calculator. Then I'm going to be looking at one of us is an exponential growth. One of them is a horizontal line. So that's what I'm expecting to see when I graph this. Now, to graph this, though, I've got to come up with a reasonable scale so I can see it. So your X is your time in hours. It's at 10 to start with, and I'm going to double till I get to 1,000. Okay, now that might feel like it's going to be a while, but really when you start doubling things, it starts growing quickly. So I'm going to go with a max. I'm going to go from 0 to 10. And I'm just going to scale it by ones. Now, the Y values are how many bacteria there are. And I'm shooting for 1,000 bacteria. So maybe I'll put in a max up here of 1,500. Just giving myself some buffer in there. All right. And then if I'm going by 1,500, I'm probably going to scale it by maybe 100 as I go. When I graphed this, I've already done it. I graphed it and it came up here and it was this beautiful exponential growth. And then it had this horizontal line right here at 1,000. And I was looking for this ordered pair right here. And so I went to my calculator and I did the whole second trace. And I went to intersect again, number 5. And I usually, once you start doing this, I mean, it's first curve, second curve. It automatically goes from the first to the second. I even press enter through the guess because there's only one intersection. So I don't care about the guess. So I just hit enter, enter, enter. And here is what I've got. I got a 6.64. 385, blah, blah, blah. Okay, so what did I just find? Okay, that is my time. That is my time in hours, but they want me to answer it in hours and minutes. So I sort of need this full value again. And I don't know if you knew this or not, but you can actually salvage this number from a graph back over to your home screen. So if you right now are looking down here and it's saying X equals this 6.64 number and it says Y equals 1,000. Okay, right here at this stage, if you just do a quick second quit, it will take you back to your home screen. And then what you're wanting is that answer that it was telling you right here, that X value. So if you hit second little negative key, that's underneath the 3, that's really second answer. If you hit second answer, it will pop up that full value for you so that you're not having to write it all down and retype it all back in. All right, so knowing that now, next time I'm probably not going to write this many decimals. I'll just write a couple decimals and then I'll use this feature so that I have the full value. So here's what I know right now. I know that it's going to be 6 hours and then it's 0.643585 of an hour. These are not minutes here. This is a portion of an hour. It's over half of an hour, it looks like. And it's almost 2/3 of an hour, but not quite. But I'm supposed to find exactly how many minutes. So here's my trick to this. I know that it's going to be 6 hours. My goal is to figure out what this 0.64 number is going to get me. What part, how many minutes does that equate to? So what I do with me sitting there with this number right here on my calculator, I immediately subtract 6. And the point of doing that is to get rid of this guy right here. I don't need that. All I really want is this decimal part. And so that's kind of the quickest way, is you just subtract off the whole number. And then what I'm going to do is and I'm stopping at 5, but my calculator has the full value there. I'm just going to take that times 60. If I take that times 60, I get 38.63. Now I could do that again. Well, let me go ahead and write my answer. It's going to be 6 hours, and I'm only going to minutes, so but I can have part of a minute. It's okay to have part of a minute. So I'm going to go ahead and round to the hundredths. If they wanted me to go to seconds, I would subtract 38 off of that and then take the 0.63 full value times 60 to get my seconds. But they didn't want that. So there's my answer. Okay, a lot of calculator stuff that you need to be familiar with on this. Okay, that's all I have. So your homework, probably a worksheet, I guess, just depends. Hopefully you have that. If not, look in Google Classroom. All right, have a great day.